If you're listening to fall asleep, you're in the right place. Let your shoulders soften. Breathe slowly. Tonight, we're going to drift across deep time, past the familiar constellations of human history and into an older story, written not in ink, but in stone. The Earth is about 4.5 billion years old, and in many places the crust keeps a careful diary. Sand hardened to sandstone, mud to shale, shelf fragments to limestone, stacked in quiet pages. Volcanoes and seas, warm spells and ice, lives that bloomed and vanished, all of it recorded. Except there's a problem. In the middle of this grand book, there's a chapter, really an entire volume, that's missing. 1 billion years gone, as if a cosmic hand tore out the pages and blew them into the wind. This gap has a name now, the Great Unconformity. It is not a subtle edit. The missing interval is longer than the time complex animals have existed, longer than the span from the first trilobite to the present day. Imagine opening a family album and finding that all the photos between toddlerhood and middle age have vanished. You would still know you exist, you're here after all, but you'd be haunted by how much you cannot see. That is what the rocks tell us. We were here, and also, so much is gone. Our story begins on a scorching August day in 1869. The American Civil War has ended. A ribbon of rail now stitches east to west. And in a maze of stone the world had not yet mapped, a one-armed geology professor is preparing to launch 4 wooden boats into the unknown. His name is John Wesley Powell. He lost his right arm at Shiloh to a mini ball, but he kept a stubborn curiosity that even gunfire couldn't touch. He was supposed to teach, to grade exams, to give safe lectures about safe rocks to students who might rather be elsewhere. Instead, he scraped together a crew of volunteers and supplies for what many believed was a suicide expedition. Follow the Green and Colorado rivers wherever they led, no matter what. Close your eyes and picture it. 10 men, provisions for months, no GPS, no satellite phones, no rescue planes. Just pine, planks, oars, and the echo of water in a canyon no map dared to name. They push off. The river grabs them with a cold hand and pulls them downstream. Walls of red and purple rise higher with every bend. Day after day, rowing, scouting rapids, lowering boats on ropes, losing food to upended cargo, patching hulls, trading jokes in the dark to keep fear at bay. The crew writes in diaries with cramped, weather-stiff fingers. Powell sketches with his left hand, pencil clicking against paper as the river speaks. Powell is not just a river captain. He is a reader of rocks. And the canyon is a library. In geologic language, older rocks generally lie beneath younger ones because time stacks its sediments from the bottom up. Each layer is a page, each page a quiet report. Here there was a shallow sea. Here, muddy floodplains. Here, dunes march like waves. At first glance, the Grand Canyon is simply beautiful. Bands of orange and vermilion, shadow and light. But to Powell is also syntax and grammar. He traces contacts where one layer meets another, naming them, measuring them, building a story. The river's song becomes a sentence he can translate. Then, somewhere in that labyrinth, Powell's eye catches a line. A razor-straight boundary slicing across the face of time, where 2 utterly different worlds touch. Below the line, dark, crystalline basement rock, granites and gneisses, twisted, folded, and scarred by ancient heat and pressure. Above, neat, horizontal beds of pale, sandstones and shales, almost modern by comparison, lying calm and level. Between them, nothing, no gentle staircase of layers that should, by rights, connect the deep past to the more recent. It is a clean break, a quiet cliff in the record. Geologists call such a break an unconformity, a gap where deposition stopped or older layers were removed before younger sediments arrived. Unconformities are common. Rivers scour, glaciers scrape. Mountains rise and fall. But this one is different. When Powell and those who followed did the arithmetic, it seemed impossible. The basement below, the contact dates back well over 1 billion years. The first sediments above are roughly half a billion years old. In between lies a gulf of more than 1,000 million years gone. Imagine reading a novel where chapter 5 flips straight to chapter 19, and somehow the characters are alive, changed, complicated by events he never saw. For many years after Powell's voyage, the Great Unconformity would be discussed in field camps and lecture halls, in notebooks smudged by thumb and rain. Was this a local quirk of the Colorado Plateau? A trick of erosion in one canyon among many? As more teams fanned out across the Scottish Highlands, the Canadian Shield, the ancient cores of South Africa, the Flinders Ranges of Australia, the same strange seam appeared. Old rock, young rock, and in between an absence that speaks. The more geologists looked, the more they found a pattern, not a fluke. A global scar. If you're settling deeper into the pillow now, that's okay. Let your breathing match a slow river. We'll take the turns gently, because the mystery is not only what is missing, but why. The interval erased coincides with a time of profound transformation, when the first complex cells emerged, when oxygen accumulated in the seas and sky, when the stage was being set for complex animals to appear. The missing pages fall precisely where we most want to read. Early explanations leaned on familiar culprits. Ice can be a ruthless editor. Glaciers sandpaper mountains to dust. Perhaps, said one generation of scientists, the world froze over in a snowball Earth event and scraped the continent's border. Later, another generation pointed deeper to the engine room of the planet. Continents collide to build supercontinents and tear apart to die. In those convulsions, our force is strong, enough to lift new Himalayas and then grind them away again. Which is it? Ice or fire? A single winter of the world, or a long tectonic unmaking? We're not there yet. Tonight, part 1 is about seeing what Powell saw and recognizing what it means for the story to come. Consider the courage of noticing a line on a wall and admitting it rewrites the book. He could have rode past. He could have admired the colors and kept going. Instead, he placed his hand on the boundary, felt the texture shift under his fingers, and let the question anchor him. Where did the time go? Here's a gentle image to fall asleep with. The boats are pulled up on a gravel bar. A small fire crackles. Tin cups rest in coals. The canyon swallows the day's last light and reveals a river of stars. The crew talks in, low voices about rapids ahead. Someone laughs. Someone skips a stone that clacks and vanishes. Powell sits with his diary, sketching that crisp line by firelight, old, new, and the silence between. Above them, Orion climbs. Below them, the Colorado breathes in the dark. And right there, in the quiet between heartbeats, a new chapter of Earth science begins with the simplest observation. 2 worlds touching and 1 billion years missing. Before you drift off, a small invitation the original storyteller liked to make. If you're awake enough, whisper your city and the time. Lisbon at 2 a.m., Lincoln at 8 p.m., Bangkok at midnight. The math checks out. The strangeness remains. We're all listening together, across different nights, to a planet that keeps secrets well. In the next part, we'll step closer to the boundary itself, how geologists measure time in stone, why older lies beneath younger, and how a scar in the Grand Canyon grew into a globe-spanning mystery. For now, breathe. Let the river carry you. The line is there. The question is waiting. And the answer, like sleep, will arrive in its own slow, inevitable way. Settle deeper into your blanket. Tonight we step closer to the line Powell saw carved across the walls of the Grand Canyon. Imagine yourself standing with him on a ledge of warm stone. The echo of the Colorado below, the sky wide and merciless above. The air is dry, carrying the faint mineral smell of dust and heat. Around you rise walls of color, stacked like an endless cake. Chocolate reds, honey yellows, and pale pinks that glow in the evening sun. But if you look carefully, you notice what Powell noticed. The cake is missing layers. The recipe has gaps. Geology is, at heart, the art of reading time turned into stone. Every layer of sedimentary rock begins as something soft. Mud settling in a quiet lake, sand piling up on a beach, lime-rich shells blanketing a shallow seafloor. With pressure, time, and chemistry, these layers harden, keeping fossils, ripple marks, even raindrop impressions. Geologists read them like sentences. Here, the sea advanced. Here, dunes rolled across a desert. Here, strange creatures left their tracks. Older rocks lie beneath younger rocks, unless something extraordinary happens. In the Grand Canyon, extraordinary is exactly what Powell saw. Beneath his boots stretched the basement complex, ancient granites and gneisses, hardened in Earth's early fires, bent and fractured by unimaginable pressures. These rocks had endured more than 1 billion years of history. Mountain building, volcanism, the rise and fall of oceans. Above them, however, sat horizontal beds of sandstone, clean, crisp, almost fresh by comparison. Their grains, once part of beaches and river deltas, formed hundreds of millions of years later. And between the two, nothing. No gradual transition. No middle chapters. Just a boundary of flat, sharp contact, as if the story jumped forward in time by 1 billion years. This was the Great Unconformity. Powell knew enough geology to understand the implications. To stand at that line was to stand in two different worlds. Below, rocks over 1.5 billion years old. Above, rocks around 500 million years old. The missing gap was longer than the history of animals, longer than the rise of multicellular life itself. Imagine a library shelf where Volume 2 ends with Once Upon a Time, and Volume 3 begins with, and then the world was full of cities, rivers, and kings. You would know there had been a middle volume, but it would be gone, leaving only the echo of its existence. Later geologists would put numbers to the gap, running their fingers across the line, hammering samples, testing minerals in laboratories. They would confirm what Powell only suspected: more than 1 billion years missing. Not eroded in one canyon, not erased in one accident, but absent across entire continents. Wherever explorers went, in North America, Australia, Africa, Scotland, they found the same silence in stone. Old rock, young rock, nothing in between. How can so much time vanish? To understand that, we need to think about what Earth was doing during those missing years. This wasn't a quiet time. Far from it. Between 1.6 and 0.6 billion years ago, Earth changed dramatically. The first complex eukaryotic cells evolved, carrying within them the seeds of plants and animals. Oxygen began to accumulate in the seas and sky, transforming chemistry and paving the way for multicellular life. The continents themselves fused into a giant landmass, Rodinia, that later tore apart in violence. And at least once, maybe more, the planet froze nearly. Solid from pole to pole, a snowball Earth. These are some of the most crucial events in Earth's history. And yet the rock record, the book we rely on to tell the tale, is gone. Think of it like this. Imagine trying to understand how humans went from painting animals on cave walls to building cathedrals and inventing the printing press without any record of the millennia in between. You would be left with mysteries. When did writing begin? How did farming arise? Where did cities first appear? The Great Unconformity is like that. On one side of the line, a young world with only single-celled organisms. On the other side, a planet bustling with trilobites, shellfish, reefs, and predators with eyes. How do we leap from one to the other? For Powell, the questions were thrilling but also overwhelming. He had set out to map rivers and canyons, to fill in blank spaces on the American map. Instead, he had stumbled on a blank space in time itself. He couldn't have known that his discovery would ignite over a century of debate. Some would argue glaciers had scoured the continents clean. Others would argue tectonic forces tore apart supercontinents and exposed vast landscapes to erosion. Some would even suggest both processes work together, ice sharpening the knives that tectonics first raised. As Powell's boats scraped forward through rapid and whirlpool, he might have glanced again at that scar in the canyon wall, wondering what it meant. His men were hungry, their clothes in tatters, their shoes wearing thin. They could hardly know they were drifting past one of Earth's deepest secrets. Yet Powell sketched, measured, and wrote. He carried the question with him, knowing future eyes and tools would be needed to chase the answer. Let's pause here. You might hear your own breath now, slow and steady, like a river's current. The Great Unconformity is not only a geological puzzle, it's also a meditation on absence. Sometimes what's missing is as important as what remains. The canyon wall says, "Here's what I lost." And in that loss, we find our wonder. In the next part, we'll follow the mystery outward, from one canyon to a planet-wide scar. We'll trace the missing years to Scotland, Canada, Australia, and beyond. And we'll begin to explore the earliest theories. Could an ancient ice age have sandpapered the continents clean? Could entire chapters of Earth's memory have been erased under a sheet of ice kilometers thick? The silence grows louder as we follow it across the world. Close your eyes and imagine leaving the Grand Canyon behind. You pack away Powell's field notes, fold the canvas tents, and push the boats back into the Colorado. But this time, the journey is not along a river. It is across oceans and continents. Because the missing time Powell discovered in Arizona was not unique to that desert canyon. It was only the beginning of a far bigger story. One written on every continent, whispered in stone from Scotland to Australia, from Canada to South Africa. The Great Unconformity, it turned out, was not a local quirk. It was a global scar. Let's start in the Scottish Highlands. There, among windswept hills and lochs shrouded in mist, lies a contact geologists call the Hutton Unconformity. Long before Powell, in the late 1700s, James Hutton, sometimes called the father of modern geology, noticed something peculiar. In cliffs at Sitkar Point, tilted layers of ancient gray sandstone lay beneath younger horizontal layers of red sandstone. The older rocks had been folded, uplifted, and eroded flat before the younger rocks were deposited. Hutton realized this meant entire cycles of deposition, mountain building, and erosion had occurred before the newer layers appeared. The Earth, he concluded, was far older than anyone imagined. In fact, he said, it showed no vestige of a beginning, no prospect of an end. What Hutton had glimpsed in Scotland was a cousin of what Powell later described in the Grand Canyon. 2 centuries apart, two geologists saw time itself fractured, now crossed the Atlantic to Canada's ancient shield. Here, polished rock stretches across forests and lakes. Geologists hammer the surface and find the same pattern. Billion-year-old basement rocks capped directly by much younger sediments, with an abyss of time missing. Travel to Australia, and again you find it. Crystalline rocks billions of years old overlain by Cambrian sandstones only a few 100 million years old. The same gap repeats, like a haunting refrain, everywhere scientists look. Old world, new world, and silence between. Pause for a moment and feel the weight of that. This is not a local erosion event, not a river valley secret. It is something planetary. Earth has lost 1 billion years, and the absence stretches across every continent we know. So what could erase so much history? Early theories reach for the most dramatic culprit imaginable: ice. The idea of a snowball Earth began to circulate. Picture the planet 700 million years ago. Instead of the familiar blue marble, imagine a frozen sphere hanging in space, white and cold, wrapped in ice from pole to pole. Glaciers kilometers thick covered continents. The oceans froze nearly solid. Even at the equator, tropical seas lay under ice. If such glaciers advanced across the land, they would grind and scrape with unimaginable force, erasing layers of rock like a carpenter sanding wood. Could this have happened on a planetary scale? Could the missing billion years have been scoured away by an Earth locked in deep freeze? The timing seemed to fit. Geological evidence suggested global scale. Glaciations occurred during the very interval the unconformity spans. Dropstones, large rocks carried by icebergs and dropped into fine marine sediments, were found in equatorial deposits. Erased the billion years Powell found missing. For decades, the snowball Earth hypothesis carried weight. It was dramatic, almost poetic. The world frozen solid, glaciers sanding continents smooth, wiping away eons of history. And yet, doubts remained. If Earth froze completely, how did it thaw again? Why didn't it stay locked in ice forever, reflecting sunlight into space? And why did the missing years not vanish at exactly the same time everywhere? Some places lost rock earlier, some later. The pattern was too complex for a single, all-erasing ice age. Another camp of geologists pointed away from ice and toward fire. Deep within Earth, continents are restless. They gather into supercontinents, vast fused landmasses, and then, over hundreds of millions of years, they split apart again. Each cycle creates enormous mountain ranges, tears open new oceans, and unleashes volcanic chaos. Could the breakup of a supercontinent have exposed rocks to such relentless erosion that entire chapters of Earth's history disappeared? Could tectonics, not glaciers, be the hand that tore the pages? The truth, as always, seemed to live somewhere between. Ice had its role. So did tectonics. Snowball Earth could explain some erasure. Supercontinent breakup could explain others. But no single theory fit the whole globe neatly. Instead, the Great Unconformity began to look like the fingerprint of many overlapping processes, ice advancing and retreating, mountains rising and crumbling, oceans opening and closing, all colliding across hundreds of millions of years. For the listener drifting towards sleep, think of it this way. Imagine Earth as a manuscript written in layers. Sometimes the author erases a line with ice. Sometimes pages are torn out during tectonic upheaval. Sometimes whole sections are rewritten by fire and flood. What Powell discovered is that between one chapter and the next, Earth revised so much that the original words are gone. Only the binding remains. And here is where the mystery deepens. Those missing years are not random. They coincide with a time when life itself was transforming. This was the age when single-celled organisms learned to cooperate, forming the first truly complex cells. Oxygen levels shifted slowly at first, then dramatically. Biology and geology were dancing together, but the music is missing. The record skips, and we do not know the steps. So when you imagine that flat line in the canyon wall, don't see it as empty. See it as full of questions. How did early cells breathe? When did algae bloom across shallow seas? Did primitive organisms rise and fall in ways we cannot imagine because the rocks that held their fossils are gone? Concrete. The birth and death of Rodinia, an ancient supercontinent whose violent breakup may have been the true sculptor of the Great Unconformity. For now, let yourself float with the thought. Earth keeps secrets well. Sometimes it tells its story in stone. Sometimes it erases a billion years, leaving us only with silence and wonder. Breathe slow, as if your chest were an ancient tide. Tonight we walk backward through deep time, back past the dinosaurs, past trilobites, past even the first worms wriggling in Cambrian seas. We step into a world so alien that the sky itself seemed a different color. This was a billion years ago, during the age of Rodinia, a supercontinent unlike anything we see today. To picture Rodinia, imagine dragging every continent, North America, Africa, Asia, Australia, Antarctica, across the oceans and squeezing them together like puzzle pieces forced into one. No wide Atlantic, no Indian Ocean, no scattering of island arcs. Just one massive landmass, bigger than anything that exists now, wrapped in a single, endless ocean. From space, it might have looked like a great stone shield floating in darkness, fringed by waves. Rodinia was enormous, and enormous things change the planet around them. When continents cluster, the circulation of atmosphere and ocean shifts. Vast interiors dry out, becoming deserts where rain never falls. Coastal zones shrink, reducing shallow seas where sunlight and nutrients mingle. Winds sweep across open rock plains, carrying dust and heat. The climate tilts. Life, still mostly single-celled microbes, faces a world of extremes. But even supercontinents cannot last. Beneath Earth's surface, tectonic plates grind and stretch, pulling against each other in slow, irresistible motion. Heat wells up from the mantle, straining the seams. And after hundreds of millions of years, Rodinia began to tear apart. Not all at once. No, supercontinents rip like fabric, unraveling in stages over spans longer than the entire history of mammals. Around 750 million years ago, cracks opened across Rodinia's crust. Mountains thrust skyward as rock was forced up. Valleys collapsed into widening rifts. Volcanoes bled lava and ash. Imagine earthquakes so vast they made the largest ones today feel like distant. Tremors. When mountains rise, they seem eternal. But in truth, they are fragile, always at war with wind and rain. Rodinia's newborn peaks, perhaps higher than the Himalayas, were naked rock. For land plants had not yet evolved to hold soil together. There were no forests to soften rain, no roots to lock slopes in place. Storm after storm, drop after drop, erosion began its relentless work. Rivers swelled with silt, cutting valleys, carrying whole mountains grain by grain into the sea. The process lasted not years or centuries, but millions upon millions of seasons. This erosion is one of the keys to the Great Unconformity. As Rodinia fractured, vast regions of rock that had lain buried for eons were suddenly exposed. Mountains crumbled, their debris washed away. Layer after layer was stripped, erasing the geological record page by page. In some places, up to 8 kilometers of rock vanished. Think of that. The entire vertical height of Mount Everest. Not once, but multiple times, worn away and carried to the ocean. Scientists now suspect that this slow-motion cataclysm, Rodinia's violent breakup, was the hidden hand behind much of the missing billion years. The evidence comes not just from missing rocks, but from the survivors, tiny crystals of zircon. Zircon is a mineral so durable that it can endure heat, pressure, even chemical assault. Within each crystal lies uranium that decays into lead at a fixed pace, like a clock ticking invisibly over millions of years. By measuring zircon, geologists can tell when rock cooled, when it was buried, when it was exposed. And here's what zircon's from. Around the world reveal, between 1 billion and 500 million years ago, rocks in many regions cooled rapidly, as if enormous blankets of overlying rock had suddenly been stripped away. The zircons are like whispers, each one telling the same story: uplift, erosion, exposure. This wasn't a single event. It was a sequence, a chain reaction unfolding across the globe as Rodinia fell apart. Different fragments were uplifted at different times, creating a patchwork of missing history. Now, add another ingredient to the story: chemistry. When fresh rock is exposed, it weathers quickly. Rainwater, slightly acidic with carbon dioxide, reacts with minerals like feldspar and olivine. This process consumes atmospheric CO2, pulling greenhouse gas out of the air. Less CO2 means cooler climates. Cooler climates mean more ice. More ice means more erosion, as glaciers carve their way across the surface. It is a feedback loop, tectonics exposing rock. Weathering cooling the planet, glaciers amplifying the erosion. The missing billion years may be the combined result of Rodinia's breakup and the icy hand of climate responding in kind. The consequences of this geological storm were not limited to stone. As mountains crumbled, nutrients, phosphorus, iron, nitrogen poured into the oceans. Imagine seas suddenly rich with fuel for life. For 3 billion years, Earth had been ruled by microbes, evolution sluggish, complexity rare. But now, with oceans fertilized by the ruins of Rodinia, biology was given new tools. Nutrients fed algae. Algae pumped oxygen into the seas and skies. The stage was being set for a biological revolution. Pause here and picture Earth around 700 million years ago. Great mountain. Ranges crumble in silence, their dust feeding rivers that empty into shallow seas. The seas glow green with algal blooms. The atmosphere stirs, oxygen slowly rising. The continents drift apart, their fragments gliding like rafts into new positions. Volcanoes thunder along rift valleys, their ash clouds blotting out stars. And above it all, the planet edges toward a deep freeze. Snowball Earth, the coldest chapter it has ever known. Rodinia's death was not quiet. It reshaped the planet's surface, climate, and future. It may be the reason Powell, centuries later, found 1 billion years missing in canyon walls. In the next part, we'll look more closely at the scientific sleuthing, how zircon crystals, helium atoms, and the new field of thermochronology revealed. The fingerprint of Rodinia's breakup, and how these tiny minerals hold the memory of Earth's most violent makeover. Lie back and imagine holding in your palm a crystal smaller than a grain of sand. It looks ordinary, maybe like a fleck of glitter caught in the light. Yet inside this tiny fragment lies a secret. It has recorded 1 billion years of Earth's memory. That crystal is zircon, one of geology's most powerful storytellers. To unlock the mystery of the Great Unconformity, the vanished billion years, we must turn to these humble, ancient timekeepers. The geological time capsule. Zircon is nearly indestructible. Unlike most minerals, it resists heat, pressure, and chemical attack. A zircon crystal that forms deep in Earth's crust can survive being buried, melted, uplifted, and eroded, carrying a record of its journey the way tree rings carry seasons. More importantly, zircon contains uranium atoms. Over time, uranium decays into lead at a perfectly predictable rate, a clock that ticks silently through millions and billions of years. By measuring the ratio of uranium to lead, geologists can read the crystal's age with remarkable precision. But zircon tells more than just when it was born. As it cools, it can trap helium atoms in its lattice. Over time, those atoms leak away depending on temperature. By studying helium retention and release, a method called thermochronology, scientists can reconstruct not just the crystal's birth, but its journey. When it cooled, when it was buried deep under hot rock, and when erosion stripped the overlying layers away to bring it back near the surface. In other words, zircon crystals are like black boxes in an airplane. They record the hidden history of Earth's crust, reading the Great Unconformity. When geologists applied thermochronology to zircons from rocks beneath the Great Unconformity, the results were astonishing. Across North America, Australia, and beyond, zircon showed the same story. Rapid cooling events occurring between 1 billion and 500 million years ago. This cooling could only mean one thing: huge amounts of overlying rock were suddenly removed. Mountains were skinned bare, exposing the ancient crust to the cool surface. And the timing lined up perfectly with Rodinia's breakup. As the supercontinent cracked apart, tectonic forces thrust mountains upward, only to have them eroded down over millions of years. In some places, entire vertical kilometers of rock were stripped away. Imagine standing at the Grand Canyon's rim and realizing that once 8 kilometers of stone lay above what you see today, years of geology. Erased, carried as sediment into ancient seas. Erosion on a planetary scale. The scale is almost impossible to grasp. In North America alone, estimates suggest enough rock was eroded during this time to fill a mountain range larger than the Himalayas. Add an erosion from every other continent, and the numbers become staggering: billions of cubic kilometers of rock destroyed. All of it gone, leaving behind a silence in the rock record that Powell first touched in 1869. But erosion was not uniform. Zircon evidence shows that different regions cooled at different times. Some areas began eroding as early as 1 billion years ago. Others were stripped closer to 700 or even 500 million years ago. This patchwork tells us the story wasn't one cataclysmic scrape like glaciers grinding the world flat, but rather a long, staggered process. Different fragments of Rodinia lifted and eroded in sequence, each adding its contribution to the missing billion years. Ice, fire, and feedback. Here is where the story grows more intricate. As fresh rock was exposed, chemical weathering accelerated. Rainwater, enriched with carbon dioxide, reacted with silicate minerals, locking away greenhouse gas. The atmosphere cooled. Ice advanced. Glaciers ground across mountainsides, adding their own force to the erosion. Volcanic eruptions during Rodinia's breakup pumped more gases into the sky, shifting climates again. The result was a complex dance of tectonics, chemistry, and climate, each amplifying the other. Some scientists now think this is why the Snowball Earth episodes were so severe. The breakup of Rodinia exposed enormous amounts of rock to weathering, which drew down atmospheric CO2. Without enough greenhouse gas to trap heat, the planet froze. Once ice sheets expanded, they reflected sunlight, making Earth colder still. The world became a feedback loop, spiraling toward a frozen state. A fragile balance. Pause for a moment and picture this feedback at work. A mountain range rises and is stripped of its skin. Rain leaches minerals, drawing carbon dioxide out of the air. The planet cools. Ice thickens. Glaciers grind the landscape, releasing yet more fresh rock. More weathering, more CO2 drawn down, more cold. Each cycle feeds the next until the Earth itself teeters on the edge of habitability. And yet, without this violent process, life as we know it might never have arisen. The nutrients released by erosion, phosphorus, iron, nitrogen, fertilized oceans. Algae bloomed. Oxygen spread. When the planet thawed, seas brimmed with potential. What looked like destruction became creation's hidden hand. The whisper of zircons. All of this, the missing billion years, the erosion of mountains, the freezing of oceans, comes to us not from grand monuments or obvious fossils, but from crystals no larger than dust motes. Zircons whisper across time, saying, yes, the world was torn apart here. Yes, the rocks above me were carried away. Yes, I remember when the crust cooled, when the air thinned, when ice took hold. It is humbling to think that entire revolutions in our understanding of Earth rest on listening to these tiny voices. Without them, we might still imagine glaciers alone erased the billion years. With them, we see a fuller picture: tectonics, weathering, ice, and time, all conspiring together. So tonight, as you drift toward sleep, imagine holding one of those crystals. It has survived 1 billion years of heat, pressure, erosion, and burial. Yet it still glitters faintly, still carries memory. Inside, it keeps the story of a world both destroyed and remade. In the next part, we'll step back into the ice itself, into the snowball Earth. Episodes when glaciers reached the equator, oceans froze, and survival itself hung in the balance. We'll explore how close life came to being extinguished and how the deep freeze may have been the crucible that set the stage for evolution's most dramatic leap. Let your breath fall into a slow rhythm. Cool air in, warm air out. Imagine now that the entire planet takes that same breath, but instead of warmth, it exhales into silence and frost. This is the story of Snowball Earth, perhaps the coldest chapter in our planet's long history, and one that sits right inside the billion years missing from Powell's Canyon Wall. A white marble in space. 700 million years ago, Earth looked nothing like the familiar blue marble we know. Picture instead a sphere wrapped in ice, gleaming like a frozen pearl against the black of space. Glaciers stretched from pole to pole. Even the equator, a belt where sunlight should have delivered heat, was locked beneath sheets of ice a kilometer thick. Oceans froze almost to the seabed. Winds howled across barren plains of snow where once there had been shorelines. For decades, geologists debated whether Earth could truly have frozen so completely. But evidence stacked up. Dropstones, large boulders carried by icebergs and dropped into fine ocean mud, found in layers that should have been tropical. Scratches in bedrock, called striations, carved by glaciers that had no business being near the equator. Chemical signals in ancient rocks, pointing to oceans sealed under ice, cut off from the atmosphere above. It seemed undeniable. The world had been a snowball, the puzzle of escape. Yet here we are, alive. If Earth froze so deeply, how did it thaw? Models show that once ice covers the planet, it reflects sunlight back into space. More ice means more cooling, a runaway process. Left unchecked, Earth should have remained frozen forever. The likely savior was fire, volcanoes rumbling beneath the ice, still venting gases into the sky. Carbon dioxide built up over millions of years because with oceans sealed under ice, there was no way for the gas to be reabsorbed. Eventually, greenhouse gases thickened the air enough to trap heat. Slowly, cracks opened in the ice. Glaciers retreated. The frozen seas steamed and churned, releasing long-trapped oxygen. Earth thawed, but not gently. Imagine the violence of that melt. Ice kilometers thick collapsing into torrents. Oceans flooding continents. Temperatures swinging wildly. Storms raging as the planet lurched from deep freeze to greenhouse. The end of Snowball Earth may have been one of the most chaotic transitions our world ever endured. A planetary reset button. But what about the missing billion years? Could Snowball Earth alone have erased them? For a time, many believe so. Glaciers grinding across continents are relentless sculptors. They crush rock, carve valleys, and carry sediments far away. A global ice sheet, persisting for tens of millions of years, could indeed scrape landscapes clean, sandpapering away entire chapters of Earth's history. It was an elegant explanation. Too elegant, perhaps, because when scientists studied zircon crystals and thermochronology, the story grew complicated. The erosion didn't happen everywhere at once. Some regions showed evidence of stripping long before the Great Glaciations, others long after. The pattern was patchy, staggered. It looked less like one sudden scrape and more like a prolonged sequence of tectonic upheavals. Still, Snowball Earth had a role. If Rodinia's breakup exposed the wounds, glaciers sharpened the knives. Ice coursed across new mountains, deepening valleys, carrying debris into oceans. Together, tectonics and ice performed the erasure we see in the Great Unconformity. Life at the edge. Perhaps most haunting is the question, how did life survive? If the oceans were capped in ice, sunlight could barely reach below. Photosynthesis, the foundation of food chains, would have nearly collapsed. Some scientists suggest survival was possible in tiny refuges, pockets of open water near volcanoes where heat cracked the ice, thin melt zones where sunlight still filtered through, hydrothermal vents at the ocean floor, where chemosynthetic microbes clung to warmth and minerals. Life squeezed into these refuges, hanging on through the long freeze. It must have been a bottleneck, a near extinction. Yet from that survival, everything changed. The crucible of complexity. When the planet thawed, conditions were transformed. Erosion from glaciers had poured nutrients into the seas. Volcanoes had spiked the air with carbon dioxide, then weathering drew it back down. The climate swung from extremes of cold to extremes of warmth. For simple organisms, this was both catastrophe and opportunity. New ecosystems bloomed in the freshly fertilized oceans. Algae spread, oxygen levels rose. The chemistry of seas and skies shifted in ways that made multicellular life not just possible, but inevitable. In the crucible of snowball Earth, biology was forced to innovate. The survivors emerged into a world remade, a world that would soon explode with complexity. Rest in the ice. As you drift towards sleep, imagine lying on the surface of that frozen Earth. The sky above is dark, filled with unfamiliar constellations. The air is razor cold. Beneath you, glaciers creak and crack like the groan of an old ship. Yet deep below, in black water warmed by Earth's own breath, life holds on, tiny, patient, waiting. The billion years missing from Powell's Canyon Wall are not an empty silence. They're the sound of glaciers grinding, volcanoes roaring, cells struggling, and life preparing its next great leap. In the next part, we'll step into that leap. How the end of snowball Earth and the breakup of Rodinia poured nutrients into the oceans, creating shallow seas that became laboratories for evolution. And how this set the stage for the first strange, soft-bodied creatures of the Ediacaran period. Take a deep breath. The glaciers are retreating now. The white marble of Earth is cracking, melting, and giving way to blue oceans once more. Snowball Earth has ended. What follows is not just relief, it is revolution. The harsh freeze did not extinguish life. Instead, it prepared the stage for something entirely new. The rise of complex, multicellular organisms. Shallow seas. New worlds. As Rodinia's breakup scattered fragments of continent across the globe, shallow seas spread along coastlines. Before this time, much of Earth's ocean was deep and dark, with few places where sunlight could reach the bottom. But now, continental shelves stretched wide, providing fertile grounds for life. These shallow seas became biological laboratories. Rivers swollen with meltwater and erosion carried nutrients, phosphorus, nitrogen, iron into the oceans. The seas grew rich. For the first time in Earth's history, ecosystems had both the energy of sunlight and the ingredients of growth in abundance. Algae thrived. Microbial mats covered seafloors, and oxygen, once scarce, began to rise, altering both ocean chemistry and the atmosphere above. The first soft-bodied organisms. Around 600 million years ago, in this new world, strange creatures appeared. We know them today from fossils discovered in Australia's Flinders Ranges, Namibia's deserts, Newfoundland's cliffs. They are called the Ediacaran biota, named after the Ediacara hills where their fossils were first studied. Close your eyes and picture them. Frond-like organisms anchored to the seafloor, swaying gently in the currents, their bodies quilted like fabric. Disc-shaped forms, patterned with radiating lines, lying flat on the seabed like living coins, some shaped like ovals or tubes, soft-bodied and mysterious, with no clear heads or limbs. Were they plants, animals, fungi, or something entirely alien, a lost branch of life's tree that would vanish without descendants? Even today, scientists debate. Some may have been primitive animals related to jellyfish or worms. Others may have been evolutionary experiments, unique forms that left no heirs. What is certain is that they were the first clear sign of complexity. For billions of years, Earth had been ruled by bacteria and algae, small and simple. The Ediacaran organisms marked a turning point. Life was scaling up, trying new shapes, new strategies, new possibilities. Oxygen and opportunity. Why then? Why after the ice? The answer lies in chemistry. Glacial grinding and tectonic upheaval released vast amounts of nutrients into the seas. Microbes and algae bloomed, photosynthesizing and pumping oxygen into the water and air. Higher oxygen levels allowed for larger, more energy-hungry bodies. Soft tissues could grow bigger. Metabolic processes could support complexity. Think of oxygen as fuel. For 3 billion years, life had lived on scraps. Now, suddenly, the furnace roared. Evolution had the energy to experiment, and it did so with exuberance. Life in an alien world. Yet this was not our Earth. The continents were barren rock, silent and lifeless. No trees, no grass, not even moss to soften the ground. Winds blew dust across naked plains. Rivers carved valleys through raw stone. Only in the oceans did life truly flourish. From orbit, Earth might have looked strange. Brown continents framed by brilliant turquoise shelves of shallow seas, glowing with algal blooms. If you swam there, you would find no fish, no shells, no corals. Only mats of microbes and the ghostly forms of Ediacaran creatures, silent, soft, drifting, or anchored, their bodies pressed flat into the sediment when they died. They left no bones, no teeth, no hard parts to endure the ages, only impressions like fingerprints in ancient stone. Evolution's first experiments. What do these microbial mutts? Some simply floated, catching sunlight and currents. Few would survive long in Earth's evolutionary race, but their presence showed that complexity was possible. This was the whisper before the shout, the sketch before the painting. Soon, life would leap forward again in the Cambrian explosion, when eyes, shells, predators, and prey would transform ecosystems forever. But the Ediacaran creatures were the bridge, the first bold experiments in multicellularity after the silence of Snowball Earth. Resting with the ancients, as you drift towards sleep, imagine lying on the shore of that ancient sea. The air is thin, still low in oxygen. The land is barren, only rocks and sand. But the tide pools at your feet glow faintly green with algae. And in the shallows, the first soft-bodied creatures sway like underwater gardens. No sound, no movement fast enough for the eye to catch. Only the slow, patient pulse of life trying something new. Their fossils would one day be found in lonely cliffs, studied by geologists with magnifying lenses and wonder. But for now, they simply exist, quiet and strange, a prelude to everything that comes. In the next part, we'll step into the Cambrian explosion, a 20 million year burst of creativity when life shifted into overdrive, inventing shells, claws, eyes, and teeth, filling the seas with drama. The silence of the missing billion years would give way to a symphony of evolution. Breathe gently and imagine the silence of the Ediacaran seas giving way to a sudden rush of motion. Around 540 million years ago, the Earth shifted gears. For 3 billion years, life had been slow, simple, and small. Then, almost in an evolutionary instant, the seas exploded with creatures unlike anything seen before. This event is known as the Cambrian explosion, and it is one of the most extraordinary chapters in Earth's story, made possible, in part, by the missing billion years Powell found etched in the Grand Canyon. In the span of about 20 million years, the oceans, transformed from quiet microbial mats and soft-bodied forms into bustling ecosystems filled with animals that had eyes, teeth, shells, and complex behaviors. It was as if life had been sketching in notebooks during the missing billion years and suddenly unveiled the finished masterpiece. Fossil beds like the Burgess Shale in Canada and the Changjiang deposits in China preserve this riot of forms in exquisite detail. Here, we see the ancestors of nearly all major animal groups alive today. Worms, mollusks, arthropods, sponges, early chordates, all appearing within a blink of geological time. Consider a few of the Cambrian creatures. Trilobites, armored like tanks, with compound eyes that could detect polarized light, scuttling across seafloors in vast numbers. Anomalocaris, the first great predator up to 2 meters long, with grasping appendages and a circular mouth ringed with teeth. Opabinia, bizarre and unique, with 5 eyes perched on stalks and along. Claude proboscis for grabbing prey. Hallucigenia, tiny worm-like, bristling with spines on its back, so alien that early scientists reconstructed it upside down. Wawaxia, covered in scales and spikes, an armored pincushion creeping slowly across microbial mats. These were evolutionary experiments, some successful and destined to give rise to modern lineages, others evolutionary dead ends. Why did this explosion happen then, and not earlier? The groundwork had been laid by the billion years of tectonic upheaval, erosion, and snowball Earth. Nutrients, the breakup of rodinia, released phosphorus and other elements into oceans, fueling algal blooms and oxygen production. Oxygen. Rising oxygen levels supported larger bodies and more active metabolisms. Muscles, nerves, and eyes require far more energy than simple microbial life. Predation. Once some organisms evolved the ability to hunt, an evolutionary arms race began. Prey developed armor, predators evolved. Trilobites had compound eyes with hundreds of lenses. Other animals developed simple, light-sensitive spots. Suddenly, for the first time in Earth's history, organisms could see and be seen. This changed everything. To be visible meant to be vulnerable. Creatures evolved shells, spikes, and burrowing behaviors to hide. Predators developed claws, speed, and sharper vision. The Cambrian seas became a stage of drama. Pursuit, defense, survival. Evolution, once sluggish, now raced ahead. Even Charles Darwin puzzled over this. How could so many diverse forms appear so quickly? He called it an abominable mystery. Today, we understand that the Cambrian explosion was not life's sudden beginning, but the unveiling of complexity built during the missing billion years. Evolution had been working behind the curtain, experimenting with cells, cooperation, and oxygen use. When the curtain lifted, the cast was ready. Before the Cambrian, fossils are rare and ambiguous. After, the record is filled with abundance. Shells, skeletons, teeth, tracks. Life had become not only complex, but durable. Organisms now left hard parts that could endure, writing themselves into stone. For the first time, Earth's living story became vividly, permanently visible. Imagine drifting above a Cambrian reef. Sponges rise like towers. Trilobites crawl in swarms, their eyes glinting. Anomalocaris glides past, searching for prey, its body shimmering in sunlight. Strange worms burrow into sediment. Tiny predators swim with fins and jaws, darting like sparks in water. For billions of years, the seas have been quiet. Now, they buzz with energy, color, and intent. The Cambrian explosion set the course for all future life. Nearly every major animal body plan was established in this window of time. From then on, evolution refined and diversified, but the essential blueprints remained. The ancestors of fish, insects, mollusks, and even humans swam in Cambrian seas. The missing billion years were not wasted. They were preparation, tectonic violence, erosion, snowball Earth, oxygenation, and nutrients, all conspiring to set the stage for life's grand. We'll look at the long shadow of the Great Unconformity, how missing years, erosion, and supercontinent breakups shaped not only evolution, but the raw materials of civilization itself, or oil, and fertile soils, and how the Great Unconformity connects deep time to the human present. Let your body sink into stillness. Tonight we reach the final chapter of this journey. We began with John Wesley Powell rowing wooden boats into a canyon no one had mapped. We traced the scar he noticed in the rocks a billion years missing. We followed the story through the breakup of Rodinia, the frozen silence of snowball Earth, and the dazzling burst of the Cambrian explosion. Now, we look at what the Great Unconformity means for us today, for civilization, for our understanding of time, and for our place in Earth's story. At first glance, the Great Unconformity looks like absence, layers stripped away, a silence in the rock record. But absence is not emptiness. What was erased also created new beginnings. Erosion released nutrients into oceans, fueling oxygenation and complex life. Shallow seas opened up, becoming evolutionary laboratories. Entire mountain ranges collapsed into dust, and from that destruction came the conditions for life's great leap forward. The Great Unconformity is not just about what was lost. It's about what was made possible. Geologists now know the Great Unconformity is not unique. Similar gaps appear throughout Earth's history, linked to the cycles of supercontinents forming and breaking apart. Columbia, Rodinia, Pangaea, all left scars, unconformities where entire volumes of history disappeared. It's like a heartbeat in deep time, crash, erase, rebuild, evolve. With each cycle, life adapted, expanded, diversified. Without these upheavals, Earth's story would not have the same richness. The Great Unconformity shaped more than biology. It also shaped the raw materials we humans rely on today, metals. As Rodinia broke apart, massive hydrothermal systems concentrated ores deep in the crust. The copper in our wires, the gold in our jewelry, the iron in our machines, they trace their origins back to those ancient processes. Energy, sediments washed from Rodinia, filled ancient basins that later became reservoirs. For oil and gas, soils, the dust of vanished mountains eventually weathered into fertile ground, the base upon which agriculture and civilization would one day stand. In a sense, we live on the wreckage of Rodinia. Our cities, our technologies, even the food we grow are gifts from that billion years erased. But there's also a sobering truth. If a billion years can vanish, how much else have we lost? How many evolutionary experiments left no trace? How many climate swings, catastrophes, and recoveries are hidden forever because the rocks that held them were carried too? The sea? The rock record is not a complete history. It is a heavily edited volume, with chapters torn out, rewritten, or lost. What we hold in our hands are fragments, clues, whispers, survivors. Deep Time is less a smooth novel than a battered manuscript, still readable, but scarred. What does this mean for us, living in the thin slice of time called the present? The Great Unconformity reminds us that Earth is not stable. Continents shift, climates swing, oceans rise and vanish. To us, mountains seem eternal, but geology erases them as easily as tides erase footprints. It also reminds us of resilience. Life endured snowball Earth, near extinction, famine, and flood. And each time, it found new ways to flourish. Without catastrophe, there would have been no Cambrian explosion, no forests, no mammals, no humans. Interestingly, unconformities are not unique to Earth. On Mars, spacecraft have photographed similar gaps, places where ancient erosion removed huge volumes of rock. Across the solar system, scars in stone suggest that the violent cycles of destruction and renewal may be a universal feature of rocky planets. Earth's great unconformity, then, is not just a local curiosity. It may be a common chapter in the cosmic story of worlds. Think of it this way. Every breath you take, every heartbeat, every word spoken by humans across history, all are possible because of the billion years that vanished. Without that erosion, without the oxygen pulses, without the shallow seas, there would have been no Cambrian explosion. Without the Cambrian explosion, there would have been no fish, no reptiles, no mammals, no us. We are quite literally the children of the Great Unconformity. The scar in Powell's Canyon wall is written in our DNA. As you drift towards sleep, return once more to the canyon. Night has fallen. Powell's campfire crackles faintly on the shore. Stars crowd the sky, mirrored in the river below. Somewhere in the cliffs, that sharp line still waits. Old rock, young rock, silence between. It is not just a gap in stone. It is a reminder that creation and destruction are intertwined, that loss makes way for possibility, that deep time moves with a rhythm both terrifying and beautiful. The Great Unconformity is our origin story, written not in words, but in the erasure of words. So breathe softly now, and let that thought carry you. A billion years had to vanish so that you could be here, listening alive, part of the story.